Hello, everyone. The highest temperature scientists have ever achieved in a Large Hadron Collider is 5 trillion Kelvin. The lowest human beings have ever reached is 0.00000000038 Kelvin, which is 38 picokelvin, or minus 200.773.459.61 degrees Celsius. But is there anything hotter or colder than that? What do hotter and colder even mean? Why is one thing hotter than another? What is absolute zero? And why is its value exactly minus 273.15 Celsius minus 459.67 degrees Fahrenheit? The answers will all be in this video. Energy is the foundation of the universe. It permeates everything and governs all its mechanisms. In fact, 70% of the universe's content is energy, specifically dark energy, a type of energy that scientists know is there but can't interact with. Energy comes in many different forms and manifests itself in the motion of objects, chemical reactions, and natural phenomena. According to the world's most famous equation, E equals mc squared, even matter is just a form of energy, a supercondensed form that you can touch. If you weigh 70 kilograms, congratulations. You are a source of energy equivalent to the explosion of 1.5 billion tons of TNT, or 30 Tsar bombs, or 100,000 little boys. If you're still not impressed, humans and many animals sense temperature through sensitive nerve endings called thermoreceptors. They're sensitive enough for you to distinguish temperatures from 10 degrees Celsius to 60 degrees Celsius. But there's a problem. A kettle of water, whether frozen or boiling, still contains the same number of water molecules. The chemical formula is still H2O. So why do they have different temperatures? The core of temperature lies in the motion of atoms and molecules. All atoms and molecules are constantly vibrating, even the atoms in a block of iron or a diamond. And if you remember, any moving object has energy. It's called kinetic energy. Kinetic energy is directly proportional to an object's mass and velocity, which is why the faster an atom moves, the greater its kinetic energy and the higher its temperature. So, the temperature of an object is the average kinetic energy of its constituent molecules. In other words, the faster an object's molecules move, the greater its average kinetic energy, and the hotter it gets. When you heat up a block of ice or a steel bar, the molecules gain energy and start to vibrate faster and faster, until at some point, they break away from each other and are almost in a state of free floating. That is literally how ice melts and steel melts. But here's something few people notice. Increasing temperature is always much easier than decreasing it.
But why?
You can easily boil water to 100 degrees Celsius. You can start a bonfire and create a flame of around 600 degrees Celsius. Add coal and you can melt almost anything in your house with a 1,900 degrees fire in just a few minutes. Don't try this at home, kids. On the other hand, you need a refrigerator and a few hours to create a block of ice with a temperature of about minus 10 degrees Celsius. Why is this? Why is it so much harder to cool something down than to heat it up? And why is temperature the only measurement scale that has negative values? Why do you have minus 10 degrees Celsius, but not minus 50 meters or minus 100 kilograms? Let's like this video to buy a ticket back to 1724, the time when the Polish-German physicist and inventor, Gabriel Fahrenheit, created the temperature scale named after him, which we now know as degrees Fahrenheit. Fahrenheit set up his scale by creating 3 fixed temperature points. He placed a thermometer in a cold mixture of ice, water, and ammonium chloride salt. At the lowest temperature the thermometer reading dropped to, Fahrenheit set his reference point as 0 bar. The second reference point was the reading of the thermometer at the freezing point of water, which Fahrenheit set at 30 degrees Fahrenheit. The third calibration point, 90 degrees Fahrenheit, was defined as the normal human body temperature taken in the armpit or mouth. Today, in the Fahrenheit scale, water freezes at 32 Fahrenheit and boils at 200 degrees Fahrenheit, and the normal human body temperature is 98.6 degrees Fahrenheit. The Fahrenheit scale was the most important temperature scale in English-speaking countries until the 1970s. Today, it has been almost completely replaced by the Celsius scale, except in the US, which stubbornly uses Fahrenheit alongside imperial units like pounds, inches, and feet. The Celsius scale was first proposed by the Swedish astronomer Anders Celsius in 1742. It was the reverse of what you know today, with water boiling at 0 degrees and freezing at 100 degrees. Later, scientists inverted it, but kept the name to honor Celsius. It's clear that the Celsius scale is simpler, smarter, and more suitable for daily life. But both of these temperature scales have one flaw. They are too detached from the scientific definition of temperature that I just explained. The temperature values in both the Celsius and Fahrenheit scales are conventional, meaning they are just for convenience and don't follow any scientific rules. From a scientific perspective, temperature is like length or mass. Negative values don't exist. The lowest possible temperature is just 0 degrees. Also, from a scientific perspective, like the speed of light, it's something everyone craves but can never reach. In fact, absolute zero is a scenario you wouldn't even want to dream of. If you don't have a goldfish memory, you'll remember that temperature is directly related to the movement and vibration of the molecules that make up matter. The slower the particles move, the lower the temperature. This means that, logically, there must be a temperature point at which all movement stops completely. That is, fundamentally, absolute zero. But why is absolute zero said to be unattainable? What do we want to achieve absolute zero for? And what on earth is so special about absolute zero that we've been making it sound so dramatic since the beginning of this video? Absolute zero can be easily reached in our imagination by assuming that all the molecules of a substance stop moving. And this is where things get creepy. In 1802, the French chemist and physicist Joseph Gay-Lussac discovered that at constant pressure, the volume of a gas changes in direct proportion to its temperature. Specifically, when the temperature changes by 1 degree Celsius, the volume of the gas changes by 173 times its volume at 0 degrees Celsius. To make it easier to understand, that discovery means that when any gas is cooled down to -273 degrees Celsius, its volume will become 0. In other words, it will disappear. Yes, disappear, a word science hates.
Nope.
If Gay-Lussac were a normal person, he probably would have crumpled up that calculation and thrown it in the trash. A superstitious person might have hyped it up as a satanic formula, the end of the universe. But no, Gay-Lussac was a scientist, and he came to a different conclusion, that 9,273 degrees Celsius is the lowest temperature in the universe. Unsurprisingly, he was right. Later, the English physicist and mathematician William Thomson, also known as Lord Kelvin, developed an absolute temperature scale with no negative values, called the Kelvin scale. In the Kelvin scale, 0 degrees means absolute zero. To convert Celsius to Kelvin, you just need to add 273.15 to the Celsius temperature. For example, 0 degrees Celsius equals 273.15 K. But the more important question is, what is the true nature of absolute zero? 0K equals -273.15 degrees equals -459.67 degrees. But why do atoms and particles have to stop at 0K, at exactly 9,273.15 degrees Celsius, and not at any other value? The answer is only God knows. The exact value of absolute zero is one of many values that seem to have been fine-tuned and preset for the operation of the universe, just like the speed of light, the mass of an electron, or the number of spatial dimensions. We shouldn't and can't analyze them further, other than accepting that this is how things work in our universe. But we do know what happens to matter as it gets closer to this temperature limit. When the temperature increases, atoms speed up, break apart, and float freely, turning a solid into a liquid. This continues to happen when the temperature increases further. Matter in a state that is too constrained, even in liquid form, expands and evaporates, and then even turns into plasma, a strange but no less magical state of matter. Most of the matter in the solar system and stars exists in a plasma state. In fact, plasma, not solid, liquid, or gas, is the most common state of matter in the universe. On the other hand, if we were to perform a reverse experiment and start decreasing the temperature, the cooled particles would begin to settle and condense into a liquid, then solidify and become a solid. Inside a solid, the particles are very close together and lined up neatly, but they still continue to vibrate. Continuing to lower the temperature will cause the particles of the solid to vibrate less and less until they almost completely stop. And it's important that you remember those two words: almost completely. Just as you would need infinite energy to push a spaceship to the speed of light, absolute zero is simply unattainable. Energy is not created or destroyed, but only transferred from one form to another. When an object is cooled, it releases heat into the surrounding environment. The problem is that the closer it gets to absolute zero, the less heat the object radiates. This means that at lower temperatures, cooling becomes less and less efficient and more energy intensive. According to the principles of thermodynamics, you would need infinite energy to cool something down to absolute zero. To put it in perspective, becoming a Type 3 or even Type 7 civilization is easier than creating absolute zero. There's also another problem. At absolute zero, entropy S, the measure of disorder, would equal zero, and the third law of thermodynamics strictly forbids this. What's more, if the particles stop moving, that is, stand still, then logically we would be able to accurately determine both the particle's position and its momentum at the same time. However, the Heisenberg uncertainty principle, one of the fundamental principles of quantum mechanics, also does not allow that. In short, absolute zero is like a doll in a glass case. You can only see it and talk about it, but you can't touch it. Period. But there's nothing to be sad about, because all the most interesting things happen just before that absolute limit. In the process of deep cooling, scientists have discovered unimaginable and magical properties that challenge the laws of conventional physics. Specifically, at temperatures very close to absolute zero, some metals almost completely lose their electrical resistance. They become the legendary perfect conductors, allowing electric current to flow with almost no loss. This is called superconductivity. Gases are no less magical. Helium gas becomes a liquid at -269 Celsius. When the temperature continues to drop, a seemingly magical phenomenon occurs. The viscosity, or the resistance to flow, of liquid helium becomes zero. When you pour water into a glass, the water stays in the cup. That's the law of life. But when you pour superfluid helium into a glass, it flows. More accurately, it leaks through the extremely tiny capillaries and gaps of the glass molecules to the bottom of the cup and drips out. A layer of liquid helium can climb over the wall of its container and flow out, forming a drop underneath. It can also create a frictionless fountain that can flow forever. And what do you call that if not magic? Finally, near absolute zero temperatures have also allowed scientists to discover a fifth state of matter, something that will likely be popularized in high school curricula in the future. Congratulations, kids! Specifically, the existence of this fifth state of matter was predicted in 1924, based on the quantum formulas of the Indian physicist Satyendra Nath Bose. It is called a Bose-Einstein condensate, BEC. A Bose-Einstein condensate is a state of matter in which distinct atoms or subatomic particles slow down so much that they overlap, condense into a large cloud, and act like one giant atom. Its existence was experimentally confirmed by Eric Cornell and Carl Wieman in 1995 at the Joint Institute for Laboratory Astrophysics, JILA. Cornell and Wieman successfully merged about 2,000 individual atoms into a superatom large enough to be observed under a microscope. And if you're suddenly feeling a headache, dizziness, or lightheadedness, that's okay. Scientists have been tortured by these quantum things for more than 70 years. So what are we? In 1999, the Danish scientist Lane Howe used the fifth state of matter to tame light to the speed of a motorcycle, about 64 kilometers per hour. Even more terrifying, scientists using Bose-Einstein atomic matter slowed light from 299,792,458 meters per second down to just 0.2 millimeters per second in 2008. And they even managed to stop light for 16 seconds in 2013, and then for a full minute.
Oh my God!
We can't know how these scientific discoveries near absolute zero will change the future of human civilization. But what is certain is that a like from you can make us very happy. As always, remember to subscribe to F5M to follow our brain-boosting science content. And now, goodbye and see you again.